Hello everyone, my name is Gaurav Arora and welcome back to the 6th lecture of Spatial Statistics and Spatial Econometrics. Before we go on to this lecture, let's do a little recap of what we covered in the last lecture. As you can see on your screen, we broadly covered two topics in the previous lecture, where we formally sort of transition from a data understanding of spatial delineated products to statistical formulations and statistical modeling of those data. So, the first thing we did was broad steps in spatial statistics. So, the first step was what is spatial statistics? Well, it is a science of uncertainty of spatial nature. So, the first step was to measure or quantify disorder of spatial nature, right. So, to quantify spatial disorder, and we talked about variance, interquartile range and entropy being the measures, alternative measures that we will look at. The second step was mostly about modeling or measuring spatial dependence. The third step was from moving from correlation, that is what of location delineated statistics, to why in explaining why do we see the type of spatial trends we see, why do we see the kind of spatial dependence structures that we see. And we ended the lecture with this understanding of random functions with spatial delineations, right. So, we looked at what a random variable is and how does an understanding of random variables then translates into these jointly distributed random functions, where you have random variables located at different locations in space, and then those are moving together bound by a density function called as the joint CDF. All right. So, in today's lecture, we are going to look at a measure of spatial disorder or spatial variation known as entropy. So, here on this slide, I have a heading or a title called as entropy as a measure of variability of a random process. So, we are going to study entropy in general. From those of you coming from a statistics background, an econometrics background, economics background, might not have heard of entropy or might not have really studied it in detail. However, those coming from engineering and physical sciences might have actually studied entropy formally in your studies, right. So, it will be interesting to first review entropy as a measure of disorder and then take that understanding for a general entropy measure of variation to entropy as a measure for spatial variation, what we call as spatial entropy. All right. So, let us get started. So, in order to understand what is entropy, let us first suppose there are k states of nature. All right. So, these can be indexed by or denoted by I goes from 1 to k. All right. And each state I occurs with a probability pi. Okay. So, we have a probability measure for each state occurring in this system, a random process or random system that we are trying to study. So, basically what we have is states 1, 2, 3, 4 all the way to k, and then we also have a probability measure attached to each state, that is p1, p2, p3, p4 all the way till pk, right. And given that these are probability measures, they should follow some properties that we know from our previous training in probability and statistics, but we are going to still look at them. Each probability I must lie between 0 and 1, right, for all i's, that is 1 to k, right, and the sum of these probability measures for all k states must be equal to 1. right. So, the probabilities must sum to 1 and each probability entity must be between 0 and 1, right. Then having learnt that, we can define entropy of the probabilistic system, as under. So, we have E as the entropy measure for this system equals minus summation I equals 1 to k pi, that is the probability measure, times the log of pi. So, it is a natural log that I am taking of pi and times the probability itself, right. So, pi times log pi summed across all k states of nature and then multiplied by minus 1 is equal to entropy. This is the definition of entropy, right. We have to be a little bit careful here first of all, look, pi can take a value of 0, but then log of 0 is not defined, right. So, we say where, so to account for that we say where x log x is defined to be 0 for x equals 0. So, wherever you have probability being 0, that does not contribute to the entropy of the system, right. So, the state that does not occur does not contribute to the entropy of the system. That is the interpretation of the physical world that we get here. So, one thing we have defined entropy formally, but the system that we have worked with is a discrete probabilistic system, right. So, what we are working with is a discrete random process, right. So, this is a entropy definition for discrete random process. Okay. What if we had a nature where states were continuous? Let us look at that. So, let us call this a little aside, so that we can define entropy for the case where the states of nature were continuous. So, now the states of nature are denoted by theta instead of I. Theta is a continuous random variable which goes from theta lower bar to a upper bar. So, there is a lower bound and upper bound, and each state of theta, right, each theta will appear or occur with probability density function f of theta, right. So, each theta state occurs with a probability density function denoted by f of theta, which is nothing but also the frequency with which each theta value will appear. Then the entropy of this continuous random process will simply be given by E equals minus. So, now the summation in case of continuous system becomes integral that ranges from the lowest to the highest possible value of theta times f of theta, which is nothing but pi in case of the discrete case, and times the natural log of f of theta d theta. Okay. So, now I have a formal definition of entropy for the case when we are working with a continuous states of nature. We are working with a set of continuous states of nature. So, this is an aside. We will still sort of work with this formal setting that we began with. So, we are working with, suppose there are k states of nature, each state given by a index I goes from 1 to k, right. And for each state we have a probability of occurrence of that state I given by Pi, and for that then we define the entropy as minus summation I equals 1 to k Pi ln Pi. Okay. So, with that understanding, let us come back to our discrete case. So, first of all, when I have this idea that I could be 1 to k, Pi could be P1 to Pk, and I have an entropy measure which is minus summation I equals 1 to k Pi ln Pi, right. Notice that the states of nature may have real world interpretations, right. So, it's not necessarily a mathematical entity, these could be real world entities as well, right. So, what could be those examples? I mean, so I's could be a set of commodity prices, right. So, you could have a commodity, let us say gold, or you could have a commodity like wheat or rice, and for that commodity you have k possible price levels that appear in the real world, and each price level I can appear with a probability Pi, right. So, we can adapt this abstract mathematical notation to a real world understanding of what might I be representing, right. So, we will have set of k commodity prices with an attached probability for each price level. These may as well as a second example represent population density at various locations in a city. So, I have kept the city to be constant. Let us say we talk about National Capital Territory of Delhi, or we can talk about Mumbai, we can talk about Chennai, talk about Kolkata, or any other city that you may be interested in. Now, the population density can be considered as a random variable. You could have k different possibilities of population densities for that given city, which can be sort of where do these k different possibilities come from? Well, it depends what location are you drawing this population density from. If you are drawing it from a less sparsely populated area, let us say near the airport, an international airport, you might not have that much population density. But if you go to the city center, you might have very high population density, right. So, all these population densities may occur with attached probability, right. So, they can occur, let us say probabilistically, they could be probabilistic. Okay. Now, in that case, right, we may be interested in the mean of this random process, right. So, mean is the first moment of a random process. If I have a range of prices for gold occurring with different probabilities, I might want to know what is the average price of gold that I can expect, right. Or I might be interested in the second moment, what is the variance, can I give a measure of variance to the price of gold. If I am comparing two different commodities, I might want to know which commodity has higher variability in prices before I, for example, am trying to invest in those commodities, right. So, in that case, the mean is given by mu, which is the first moment. So, that would be expectation of I, which is given as summation I equals 1 to k I times Pi, right. And if we, and in case of, let me just use a different pen, and in case of continuous random variable, mu will be integral of theta f of theta t theta, where the integration is done from the lower bound to the upper bound of theta, right. So, this is a standard deviation of mean, right. This is something we are aware from basic statistics, exposure, right. The second moment that you may be interested in, as I talked about in a minute ago, is called as the variance. So, variance sigma squared is the second moment. So, it is given by I expectation of I squared, which is then given as I equals 1 to k I squared Pi, right. And for the continuous case, for the corresponding continuous case, and in case for the continuous random process, we can say sigma squared is nothing but integration theta lower bar to theta upper bar theta squared f of theta d theta. Okay. Now, okay, so can just rely on the definition here. Okay. Having understood that, now we know that sigma squared measures the amount or extent of variability in the random process of interest. Okay. And of course, random process of interest could be these examples like prices or population density, whatever you deem to be interesting for your own research, or depends on the analyst. Okay. Now, the thing is, the interesting thing is that it turns out that E entropy and variance sigma squared are closely related. So, what I am claiming, the claim that I am giving you here is that entropy is an alternative measure of sigma squared if we speak mathematically, and more substantially, entropy provides us a measure of variability of a random process, just like variance would do that, right. And we will see this. So, we will see how this key information piece plays out for an example distribution. So, I am going to go on to study for exponential distribution in the next slide. Okay, so, let us talk about exponential distribution now, and then figure out how sigma squared and E might be closely related. Okay. So, as a next step, we are studying exponential distribution. So, what is exponential distribution? So, we have a random variable x, right. We always begin with a random variable x, and we say that this x is distributed with exp lambda. What is lambda? Lambda is the distribution parameter. So, lambda where lambda is the distribution parameter, okay, and the density function f of x, which is the frequency or the probability of occurrence of any given value of x, which is distributed by an exponential distribution, is given as lambda times exponential minus lambda x, such that x is greater than or equal to 0, and I have already said that lambda is the distribution parameter. I mean, alternatively I could have written this as lambda e to the power minus lambda x, right. You are aware that these are we are aware that these are equivalent expressions mathematically. So, the real world instances, so what good is exponential distribution? Why do we even care about it, right? So, the real world instances that can be studied or modeled by an exponential distribution are entities like, time interval between hospital visits, okay, or visits to a national park, or visits to a national park, okay, or the visits for vacation, right. So, how frequently an individual takes vacation, an individual needs to visit a hospital for getting some treatment, or how frequently do they visit a given national park. So, if you live around New Delhi, we have Jim Corbett National Park, and we can be interested in modeling what is the time interval between two visits to the Jim Corbett National Park, right. That gives us an understanding of how frequently an individual is undertaking recreation, and then moreover, whenever they take recreation, what's the time interval with which they visit a particular national park, right. So, that to be able to model this time interval between visits for a particular kind or two events is is modeled by the exponential distribution. So, x per se, this random variable x is nothing but the the time interval between two events of interest, right. We can have different interpretations here, right. So, it could also be time spent on cab rides between points A and B, right. So, you can have two interest points A and B. You can have it from, let us say, the railway station to your workplace, from the airport to the city center, something like that. And during the day you have during different time you have different parameters like heat, pollution, traffic congestion, or availability of rides, right, and so on and so forth, which can basically deliver different time periods that it will take from me to go from the city's airport to the city center, right. How do we model this time spent? So, time spent can take a range of values, and each value that this time spent takes has a given probability distribution. In order to model this, we have this exponential distribution device at our disposal, right. So, to define finally, an exponential distribution provides a probability distribution of time between events that occur independently. So, two events, like for example rides from the airport to the city center, they have to be independent, right. So, it's not that I go to the airport and then somehow my second ride is dependent on what I did in my first ride. So, the two rides are independent of each other, right. And these are continuous events. So, I must be able to observe them happening frequently, right. It is not that they only happen once. So, if it happens only once in a while or it only happens once forever, then exponential distribution will not be able to model it. And they happen at a constant average rate. So, there is some rate at which these rides are taken or the hospital visits are taken or visits to national parks occur, and this constant average rate is modeled by the parameter lambda of our distribution. So, this is a measure for the average rate at which this happens is given by lambda. Okay. So, I mean what do we have eventually? I mean we have x is distributed as exponential lambda, and that means that f of x is lambda e to the power minus lambda x such that x is between 0 to infinity, bound open. So, x is greater than or equal to 0, and then we can write mu x, which is nothing but the first moment of this distribution, which is nothing the mean of x. So, if you have time spent on a cab ride from airport to city center, then mu x will be interpreted as the average time that is spent on this ride from the airport to the city center. This is given as 0 to infinity, that is the range of x f of x dx. This value turns out to be 1 over lambda. Similarly, I can figure out the second moment, 0 to infinity x squared f of x dx is given as 1 over lambda squared, and that will imply that the standard deviation of x is nothing but the square root of variance, that is 1 over lambda. So, one of the properties of exponential distribution is that the mean is exactly equal to standard deviation, and they are both inverse of the average rate at which this event is happening. So, the next step that we will do now, next step that we will undertake is to calculate the entropy of of the system described by the exponential distribution. Okay. So, now the entropy we know is negative of integration from 0 to infinity, which is the range of x, f of x times ln f of x dx. Okay. So, as a next step we want to first calculate this entropy. So, calculate E, and after that we will be showing, we want to show that E and sigma squared x are closely related, right. So, what we are trying to do is we are trying to verify this claim for exponential distribution. Okay. So, so what we will do is we will stop here in this lecture, and we will go to the next lecture and we will start from calculation of entropy and showing or verifying the claim that entropy is indeed closely related to sigma squared x. Thank you.